Okay, first of all, I thank the organizer to give me the great opportunity to present this talk here. The title of my talk today is Superconductivity and Electronic Properties in this infinite layer 112 and also this bilayer 327 nickelate. So it's a partial message. I hope you can get some useful message. So my name is Haihu Wen from Nanjing University in China. Okay. So this talk is a collection of many measurements, such as STM, transport, far infrared, and also TEM. So the samples, the polycrystalline samples, were grown in the group in our group, and also we get the thin film from Professor Yuefeng Li's group in our university, and also we get single crystals from Professor Meng Wan's group from Sun Yat-sen University. TEM measurement was collaborated with Dongsen Song and Binghui Ge at Anhui University, and also theoretically we collaborated with Professor Daoxin Yao and also Elia Ermin. Okay, so I will tell you the things in the following outline. So first, I will show you the earlier result on the gap feature in the superconducting infinite layer 112 thin films. Then I will show you the absence of superconductivity in the bulk of these 112 samples and its possible reasons. Then I will show you the correlation and electronic properties revealed by far infrared optics in these 327 single crystals at ambient pressure. Finally, I will show you the preliminary STM study on these single crystals at ambient pressure. Okay. So we can trace back to 1999 by Tim Rice and also later by Michael Norman and many other some other series to say that it could be possible to find high temperature superconductivity in the nickel system because the nickel is sits in the periodic table, sits in the neighbor of copper. So in that case, if the nickel 1+ cationic state, it may have this so-called out-shear electronic state 3D9, but this effort has been continued in the field, but until 2019 by Danfeng Li and in Professor Harold Huang's group, they found this superconductivity. Oh, here I'm sorry, HW. I'm sorry. So they found superconductivity from 9 Kelvin to 15 Kelvin. So that's really very exciting observation. At the same time, they showed the XRD data. Indeed, it shows that the peak shift from the so-called 113 to 112. Okay, you can see the peak shift here. So that's corresponding to the infinite layer. But at the same time, you can see that the peak seems to be broad compared to the substrate peak. Yeah, so that indicates that some kind of complex exists in the thin film. So these showed quite nice systematic data from resistivity. So this strontium doped infinite layer, no, this is the parent infinite layer without doping, shows some kind of anomalous metallic state and even insulating in the low temperature region. However, by whole doping, gradually shows the behavior like of completely metallic and shows superconductivity. And the superconducting transition temperature ranges from 9 to 15 Kelvin. And also they found this Hall coefficient. So in the parent phase, its electron charge carrier dominate, and gradually by doping holes, and this Hall coefficient across the 0 and the change sign with temperatures. And this behavior is common for cuprate and also for iron-based superconductors. Okay, so especially for iron-based superconductors, quite often to be observed. So it is quite convincing to see superconductivity at 9 Kelvin to 15 Kelvin, nowadays even reached to about 20 Kelvin. And also they showed anomalous ground state in a normal state, and also reading from the Hall effect, the charge carrier change shows probably a multi-band feature, and also reading from the critical current density, it seems that it's not from the interface superconductivity, so it's a bulk like superconductivity. And here, this slide shows a nice phase diagram they obtained on different samples, okay, shows consistently with the Hall coefficient, okay, by Hall doping. And also the phase diagram drawn by two groups, by Harold Huang's group and also by Ariando's group. So these show quite similar feature, okay, shows some kind of dome-like superconductivity with a dip in between, in the middle of the dome. So that's something puzzling. Could be the balance between the electron band and the Hall band that leads to this kind of interesting behavior. And also, Professor Jingguang Chen's group in IOP, Chinese Academy of Science, they uses hydrostatic pressure to measure on this thin film. They found that the TEC goes up continuously, even without saturation, with when the pressure is about 12 gigapascal, and with a TC about 31 Kelvin. So the TC seems to be still possible to be increased with pressure. Okay, so in our university, Professor Yuefeng Li's group produced this nice thin film, strontium-doped neodymium-113 thin film. They keep the film in the vacuum, find that sometimes the resistivity drops down, but the transition is very broad. So then we took the film to our lab and then do the topotactic treatment. Then the transition becomes sharper, okay? Nowadays, his group can produce quite nice film with very sharp transition nowadays. So then we study the thin film use STM. After the topotactic treatment, we found that the surface is very inhomogeneous. It's very rough. Okay. So we use a STM tip to treat the surface in some way. Then we protein the sample and measure at one point. Okay. Then point by point. But for second point measurement, usually we need to retract the tip and then move to another position to measure tunneling spectrum. Then most of the measurement shows that there are two types of the tunneling spectrum. One type is this kind of V-shaped. So the red curve here shows a nice dense model fitting, gives the gap in the scale about 4 milli-V. At the same time, at other positions somewhere, we can see this kind of a U shape with a gap about in a scale about 2 milli-V. So we think that this D wave-like gap should be primary, and this one should be positive gap, because now we have several Fermi surfaces. So in that case, we can assign probably the gap to different Fermi surfaces. I will show you later. Okay. So if we keep the film in a high vacuum at a temperature about 300 degrees centigrade, then we find that gradually the surface becomes more flat, and even we can see a one step of the 1 monolayer thick step here. Okay, but still we still don't have the atomic reserved the topography. But even though we can do the measurement, but now most of the tunneling spectrum shows V-shape or the mixed feature here. So you can see there is a kink on the tunneling spectrum. So we think that when the film becomes more C-axis oriented, then it's the most tunnel. We detected the tunneling current is coming from the one band, and it shows the V-shape or the mixed of the two, V-shape and U-shape. Okay. So theoretically, there have been many calculations using DFT or DFT plus U. So the major conclusion is that we have a Fermi surface, dominant Fermi surface in the KZ equals 0. With this band is dx squared minus y squared. And at the KZ equals pi, this Fermi pocket shrink into a closed one. And at the same time, we have another other two pockets, so-called beta and gamma. So this is the beta and the gamma, which come from the hybridized orbitals of the dz square with the dxy or Lansdom dxy or the Lansdom dz square. And quite similarly, Fermi surface was reported by Ronnie Somali's group. And by using the so-called spin fluctuation RPA calculation, they can get this kind of gap structure. So on this dx squared minus y squared orbitals shows the d-wave parent gap here. So that's a theory. So combining with the theoretical knowledge or results, we would like to assign the d-wave gap to this dx squared minus y squared, which is the dominant one, and on the kz equals 0 and the kz equals pi here. And on maybe the U-shaped smaller gap accommodate on this beta and the gamma Fermi surface. Okay, there are also several many kind of theoretical works about the gap structures. Also, there is some difference. Okay. It is interesting to show that later by Harold Huang and the collaborators, they use the mutual inductance measurement. They get the so-called superfluid density. The circles here show the superfluid density data, and the blue curve shows the fitting with the nodal gap. You can see that for the lanthanum or praseodymium, it shows quite nicely this superfluid density. And however, for the neodymium 112, there is a deviation. They attribute this deviation to the magnetic moment of the neodymium when you have this so-called mutual inductance measurement. Okay, so that's quite a reasonable picture. Yeah. So then I quickly to the second piece of absence of the bulk sample of the 112. So my group fabricated this 112 sample with strontium doping to neodymium site. We found the sample, the component composition looks the fitting, the XRD fitting looks quite nice. Okay, to the 112 phase, and from the fitting we can get the parameters which is very consistent, very close to the data from the film. Okay. Of course, this we first synthesize the 113 and then use the top technique to remove the apical oxygen to get this 112 strontium doped 112 phase. And we also did the local composition measurement. We found that for the nominal composition 20%, we get a central position about 16%. For the nominal one of about 40%, we get the composition about 0.19. So it seems that the strontium have been successfully doped to the grains, okay, to the lattice. So, but however, we found that there is so-called there is a deficiency about 5 to 10%. If we follow the 112 formula, but later we found that it could be induced by some extra neodymium rock salt layers in the sample, not really the nickel deficiency on the plane. Yeah, and also we see this some dark area here, which are actually the nickel segregations, because if the real composition deviated from the 112, then more nickel would segregate out from the system to form this kind of segregation. But they are not multi-connected and should not give influence on the transport property. So then we do the measurement, transport measurement. We found no superconductivity even without the whole doping, and using hot pressure to 50 gigapascal, we don't see the superconductivity. But although the resistivity drops a lot, several orders of magnitude. Very interestingly, under pressure, the resistivity shows a log T temperature dependence. We know that this kind of temperature dependence has been found quite often in the underdoped cuprate. Okay, so for the absence of superconductivity in the 112 phase, John Mitchell's group and the Phelan group also found that. I think in about this point we get the same conclusion. We also did synthesize the strontium dopes, the samarium 113 and 112. We get the quite nice phase and also the same result, long superconductive and insulating. So that's so what's the reason? Recently, we have collaborated with Anhui University. They use a high resolution TEM. So if you we go to the grains, then you can see that somewhere we have this beautiful infinite layer here, and then integrals with n equals 3, n equals 4, n equals 2, n equals even 5, n equals 1. The many kind of RP phase, and then follows this kind of infinite layers again here, okay? So in that case, we also did the local composition measurement. It seems that strontium indeed goes to the nickel side, they doped together. And according to this kind of data, we can have a cartoon picture for the sample. Actually, it is the 112 phase is caged by many rock salt boundaries, okay? And due to these integrals of the many kind of RP phase, but still in some area we can have large scale of the infinite layer phase. So then why we don't see superconductivity even from magnetization? Then we have a close look to the region with 112. Then we found that actually on the neodymium oxygen plane, even we can see this residue brightness from the apical oxygen. So we assume that could be the incomplete removal of the apical oxygen may lead to the strong buckling. So the buckling angle was determined in this area. You can see that this is the angle. So ideally the angle should be 180 degree, but angle ranges from 160 to 190. So indeed that it shows quite some strong buckling of the nickel oxygen plane. Okay, so the two reasons. One is the caged structure. The second is incomplete removal of the apical oxygen. Could be the two major reasons for non-superconductive. Then I come to the correlation and the electronic properties reviewed by far-infrared optics in this 327. So Lillian has shown you that a very good, very nice introduction. So for the 112 thin films and also for these 6512 thin films, people found superconductivity. And in this year, in last year, Professor Meng Wang's group collaboration with Professor Guangming Zhang and Daoxin Yao, they found a resistivity drop, a superconductivity signature at around 80 Kelvin, and with a phase diagram like this one. So when the in the pressure come to the FMM state and lower temperature come to the tetragonal phase, then the superconductivity comes in. Early data shows a broad transition, but later the transition becomes sharper by a set of data of Professor Haihu Wen in Zhejiang University, and also one set of data of Professor Jingguang Chen's group in IOP. And recently it was reported as superconductivity was also reported in a Japanese group with the colleagues, with Professor Kuroki and his colleagues, and also our group. And also Professor Jun Zhao's group, they found that on single crystals, so resistivity really touches zero, and the magnetization measurement shows 100%, almost 80% volume, even higher. Okay, so in that case, we think that this system shows a bulk superconductivity at least. We took the crystals from Professor Meng Wang's group and do the transport measurement. We found indeed, as other group reported, we see these two transitions. One is 150, 180, 110, and 120. So there are two transitions. So we do the optics measurement. We know that the optics measures the scattering of electrons, either intraband or interband, okay? So for intraband, near the Fermi surface, we can detect the so-called, through the KK conversion or transformation, we can get the conductivity, which is described by the so-called Drude component, okay? And through the width of the Drude component, we can determine this scattering rate, and also through the integral of this component to some cutoff frequency, we can get the charge carrier density divided by the effective mass, okay? And so our data shows like this. So this is the data measured on the 327. You can see that a little Drude component here. And there are a lot of Lorentzian terms coming from either the interband or the intraband in the low frequency area. So we separate we separate this contribution of the conductivity to different terms. From the Drude term, we found that the Drude contribution is very small. So it shows a bad metal behavior. And also the Lorentzian term, we have several Lorentzian terms can be consistently described by the interband scattering here. And also we can get a so-called K ratio. This is so-called Drude component measured and calculated. This so-called K ratio we put together with many correlated and metals. So you can see that the point sitting here, which is with a very small K ratio, close to be the extremely underdoped cuprate. So it's the parent phase, Lansdowne 214 cuprate here. So which shows a strong correlation effect. And also from the temperature dependent, we can get a scattering rate, which is consistent with this resistivity very nicely, shows a clear transition at about 120, 115 Kelvin here. And also from the plasma frequency, we can find that this plasma frequency shows a clear drop at 115 Kelvin, which corresponds to the low temperature transition, which is gapped actually. And also we found from the scattering rate, it shows two kind of behaviors. In the high temperature region shows some kind of a linear behavior. However, to the low temperature shows a beautiful quadratic temperature dependence corresponding to the Fermi liquid behavior. So in that case, we would assume that it is a dz square with a strong correlation is gapped partially and leaving the dx square minus y square ungapped, so showing this kind of uncorrelated or weakly correlated Fermi liquid behavior. Okay, then finally I come to the preliminary data from STM measurement on this 327. We got a sample from Professor Meng Wan's group for this 327. Shows resistivity shows two transitions here. Okay, and so this slide shows the tunneling measurement. We measured the tens of the tunneling spectrum. Most of them exhibit in this way. So actually, we can conclude the three major features. One is that there is a gap, a partial gap near the Fermi energy. Negative side is about minus 92 millieV. The positive side is 98 millieV. Okay, so this gapping edges may correspond to the bonding, anti-bonding edges of the 3D Z-square band. Band, or the bonding band here, and this one, because theoretical calculation shows that the bonding anti-bonding cannot be so symmetric. So in that case, we would assume that this is still the anti-bonding edge, but this one could be due to the partial gap on the bonding band. Okay, so in that case, for some reason, it looks quite symmetric, but the shape itself looks not symmetric. The second feature is that there is a quite strong residual zero bias conductance here. This is corresponding. We would assume that is corresponded to the so-called 3D x square minus y square, which is not gapped. Okay, and at the same time, we found that in the high energy scale, you can see that the density of state goes up quickly at energy about 0.7 EV, and finally with a cliff-like energy scale in about 1.4 EV. So that shows a strong correlation background. But I must say that this one is different from the cuprate, because in the cuprate, the Fermi energy is just sitting on the upper band of the charge transfer band. Okay, but now it seems that the Fermi energy is sitting in between of these two cliffs here. Yeah. So, but again, still shows that correlation effect or monotonous of the system. Okay, so based on the theoretical calculation did by Professor Daoxin Yao, we put this cartoon picture here. So the dx square minus y square band is quite widely extended. So, but for the dz square, which shows a gap here and with a gap energy in a scale about 100 millieV plus and minus. And in the high energy region, it shows the strong correlation effect. And in the group, we also successfully synthesized many 3 to 7 thin films and quite nicely picked here, even better than the 112. But upon different treating process, we found that sometimes it's insulating, sometimes it's a good metal, but so far we don't see superconductivity yet. But on this kind of film, we found that the dominant contribution is from it's positive Hall coefficient. The Hall coefficient is positive here, but it's strongly temperature dependent. Temperature dependent. Okay, so that's the preliminary from the thin film. So with that, I conclude my talk. The 112 infinite layer superconducting system seems to have multi-component superconductivity, a primary D-wave gap in a scale of about 4 millieV, and a passive S-wave gap in a scale about 2 millieV. Combining with some series, so we attribute this D-wave primary gap to the dx square minus y square orbital. The absence of superconductivity, we found the stacking fault growth of the many kind of RP phases, and we found that the 112 phase is caged by these kind of boundaries, okay? And we also found incomplete removal of the apical oxygen even in the 112 region. And in the 3 to 7 single crystals, we found a very small Drude weight, so indicated strong correlation effect, and a gapped feature occurs at about 115 Kelvin, which is according to our analysis and combining with the theory from the bonding band of the DZ square band, okay? And also from the tunneling measurement, a gapped feature with energy about 90 to 100 are observed. They may correspond to the bonding antibonding age, or as I said, the lower one, the negative biased one, could be a gapped effect to the bonding age. There is a finite density set Fermi energy we attribute to the x square minus y square, a global correlation effect with a large pseudo gap or motilus in a scale about 1.4 eV. So with that, I thank you very much for your attention.
Thank you very much, Haihu, for a very nice talk.
Okay.
So like you said, this gap sort of looks like the bonding anti-bonding of the Z squared, but that's like a structural effect. So I'm sort of looking at your STM data, wondering where the density wave gap itself is at in the STM data.
Yes, STM data shows this kind of, the value looks quite close on the positive bias and negative bias. This is about 98. This is about 92. But some experiment already show that this is there is also series also shows that there is a bonding bonding band and anti-bonding band. So we don't know whether it's completely from the density wave gapping or from the bonding antibonding age.
I mean, the bonding antibody sounds more reasonable to me because 100 millivolts would be big. I mean, the density wave transition is 100 Kelvin, so you get a delta over TC ratio, which would be huge if that was all due to the density wave. So
you mean the bonding age would be far away?
Bonding anti-bonding is just a structural effect. It has nothing to do with the density wave, right? It's just that in a bilayer structure, you get a very big bonding anti-bonding splitting the Z squared state. That would even happen without a density wave.
Yes, that's true. So that's why we cannot be completely sure whether it is it's coming from the bonding, anti-bonding, or from the density wave. So this is really a gapped feature. Right. Of course, if we say, the bonding itself certainly will show the density state,
Right.
feature near the Fermi energy, because the theory shows that this bonding age is here, the anti-bonding is here. So in
Right.
that case, the denser state would show some kind of a peaks near the Fermi energy.
Right.
Yeah.
Harold had a question.
Yeah.
Thanks. Thanks for the nice talk. It's kind of related. It's probably way too early to ask such a detail, but related to that discussion, in some systems, this kind of distorted layered perovskite has more aggressive tilting in the surface layers, right? And as far as I understand, these features are kind of correlated with this kind of tilting distortion. Do you have any sign or guess whether you have these sorts of surface rotations or reconstructions that might be non-bulk like here?
You are talking about the 112 or 327 or?
This 327, the same issue that Mike was asking about.
Ah.
So as one example, and I forgot, 214 rutheniates, right? That cleave surface has, a different surface buckling and octahedral rotation than the bulk. I was curious if you suspect there may be that instability here.
Oh, I don't have definite answer to that question. It's a good question. Actually, we have repeated this kind of measurement. So the sample is put into the chamber, even without cleaving, because the sample is not easy to cleave. And then we measure the tunneling spectrum at different positions. So we measured about maybe 100, the tenths of tunneling spectrum, which shows this kind of a common feature. So we don't know whether the surface on the top layer surface is reconstructed in some way. So far, we don't have the atomic reserved topography yet.
No,
Thank you.
Chimiao, you had a question.
Yeah, Haihu. So maybe in the same spirit of sort of going to the next layer of details.
Yeah.
If you do these multi-orbital Hubbard type of calculations, Holmes, etc., combined, the kinetic energy reduction is expected to depend on the electron filling or the number of d electrons. So I was wondering whether there's some systematics one could possibly do with this Joule weight reduction, maybe comparing 4310 with 327, or maybe oxygen vacancies, etc., as a control parameter.
Yeah, that's a very good suggestion. So we actually we also have the 327 for 4310 single crystal we can measure, and also for the 327 we can also reduce oxygen then to measure tunneling. That's a good suggestion, but
would be very
not yet
instructive.
done that. Yeah.
Okay, thank you.
Thank you.
So why don't you stop sharing your screen so Ziyang can put his talk up. But one thing, a suggestion, Haihu, that you guys could plot from the optics, plot the loss function and tell us where the plasmon's at. And from this, I'm sort of curious because the Cooper is around 1 volt. It'd be interesting to see where the plasmon's at in these materials.
Plasma age frequency, you mean?
Yeah, just take the imaginary one over
Compared
the
to the APES, huh?
Yeah, no, just from the optics, you plot the imaginary part of the loss function. The peak should give you the plasma energy.
Okay.
So you can get the plasma energy from the optics data. But anyway, we're running over here. So Xinjiang,